Okay, the second half of this unit is the rates of reaction. And so what we're going to do with this week is we're going to look at the factors affecting the rates of reaction and then the collision theory. So the factors, um, there's actually a lot to choose from, and so we're just going to kind of whittle our way through here. Um, the first one is, of course, the nature of the reactants. So what do I mean by that? Simply, um, what are your compounds that you're reacting together like? Are they ionic compounds? Are they molecular compounds? Are they in the gaseous state? Are they in the liquid state, solid state, or are they in solutions? That sort of thing. Um, that has a huge uh, effect on how fast the reaction is going to go. Secondly, how reactive those substances are. Bond strength plays a vital role here. Because in order for reactions to take place, bonds have to break, atoms have to rearrange themselves and create new bonds. And so if it takes a lot of energy for bonds to break, that's going to slow things down. If it doesn't take much energy for bonds to break, then things will go a little bit faster. Similarly, in rearranging and forming new bonds, if the new bonds require energy to form, that's going to take a little longer. If they release energy to form, that's going to go a lot quicker. So those kinds of things are essentially those how reactive substances are. An example of that would be the reaction with um, the oxalate ion with the manganate ion. In this reaction, and this is the net ionic reaction that I've got here, this reaction takes some time. It's a very slow reaction. On the other hand, if I take iron and react it with cerium in the 4 plus state, so iron 2 plus, cerium 4 plus, the transfer of electrons is all that's involved in that one, and so it's an almost instantaneous reaction. When we talk about the ionization energies, those also have a great effect on the reaction rate. So if you have a high ionization energy and a low activation energy, then you're going to have a slow reaction. Whereas if you have a low ionization energy or a high activation energy, then you're going to have a fairly quick reaction. So lithium in water, for example, that one takes a bit of time. If you've taken a piece of lithium, thrown it into some water to form lithium hydroxide, it's not a really, really slow reaction, but it takes a while to actually go. The lithium starts to skid around on top of the water, and the reaction takes a few seconds to go. If you, however, try it with a piece of potassium, um, it'll explode on you because the reaction is so much faster than that of lithium. Temperature. Increasing temperature usually results in an increased rate of reaction. Um, the odd time you have examples where that's not true is when you're dealing with gases and you've got a decreased pressure to go along with that sort of thing. But that gets a little bit more complicated. But most of the time, temperature increasing increases the rate of reaction. The concentration. Well, if you have a higher concentration, generally that increases the rate of reaction because your reactants are packed closer together within the solution. Surface area. Again, this is where we talk about how much of the surface area is exposed to reaction. In other words, it increases the reaction site when you have an increased surface area. Increased reaction sites allow for a faster reaction. If you have a homogeneous solution versus a heterogeneous mixture, that also has a tendency to have an effect on the overall rate. So if I take, for example, a piece of wood in a campfire, it takes a while to burn. But if I blow pure oxygen in there, then the wood burns a whole lot faster. Because there's that, it increases the reaction sites with the oxygen gas. Catalysts. We haven't really talked about catalysts up until this point. Catalysts have a unique ability to orient the reactants in such a way that they are able to react in a far faster rate. We'll talk a little bit more about that, but usually catalysts are used to lower the activation energy, and therefore it increases the rate of reaction. All right, so how do we kind of look at this sort of stuff? The collision theory is the theory that is primarily responsible for explaining what sorts of things are happening in terms of a reaction. The rate of reaction essentially is proportional to the number of effective collisions of reactant particles per unit time. So how do we explain that? So if I've got a mixture of these ions, so I've got some iron, I've got some manganate, I've got some hydrogen ions. When I when I can figure out how effective the collisions between these things are, so that electrons can be transferred and the manganate ion can be broken up into the Mn2 plus and water molecule and add hydroxide to the H plus, then we can end up with the water molecules being formed as well. How these things collide with each other will determine how fast this rate of reaction proceeds. So, if you've got a reaction where you've got like 14 ions that have to simultaneously collide, then that's probably not going to happen all that readily. It's going to take a while before that reaction actually starts to go and then propagates. This reaction, though, is actually fairly fast, so it's not just the collision of these 14 ions that cause the reaction to go. It's probably happening in a slightly different sense, I guess. So how do we explain that? Because if we go back to the collision theory here, the number of effective collisions. So let's kind of add something to this to allow for explaining this particular situation here. Reactions proceed via a series of smaller reactions involving collisions between 2 or 3 molecules. That would make more sense to explain that. So let's say, first of all, these two collide, and then some of this collides with what's left over from those two, and that may happen a little bit more readily. All right. So in this example here, if I have hydrogen bromide and oxygen to give us water and bromine, again, if we've got 5 molecules that have to collide here simultaneously, maybe not going to happen. However, if one of these combines with one of these, that might happen a little bit more readily. We call that stepwise reaction a reaction mechanism, where the reaction proceeds in multiple intermediate steps. Here's an example of what I mean by that. So let's say if I take a hydrogen bromide and an oxygen, and we make this kind of weird thing here. So the oxygen goes between the hydrogen and the bromine and forms this, what we call an intermediary. And then from there, in another step, it combines with another HBr and forms 2 of these guys. And then those two guys then break up and react with two of these guys to give us the water and then the bromine. Um, the mechanism is this step-by-step sequence. And then what we decide is that one of these steps in the mechanism is actually what we call our rate determining step. And that's the one that dictates the overall rate. And we end up with our final product here. So you'll notice that I've kind of built up these things here. And these intermediaries don't necessarily exist in real time. Probably you would have a hard time trying to isolate this stuff. And essentially what happens is that molecules break up in steps, and your guess as to what the steps are is as good as anybody else's. As I said, it's nigh on impossible to stop a reaction like this partway through to prove that this stuff or this stuff actually exists. So each step only requires the collision of two molecules, and then the slowest step is the one that's equimolar in the two substances, and that dictates the overall rate. All right, so what is a reaction mechanism? A series of small reactions that combine to give a final net reaction. The slowest of those steps is then what we call the rate determining step. So here's another example. We're going to combust methane. Okay, so how does this work? It's actually a really quick reaction. And if we have 1 atmosphere of each of the gases at room temperature, it's hypothesized that we get a collision at 10 to the negative 9 every 10 to the negative 9 seconds. But if you just have methane and oxygen in the room, if there's no ignition source, then the reaction doesn't actually happen. So it's not just a matter of these two things colliding and bang, you've got your, the methane is burning. If you had natural gas leaking into the room, you can smell the gas, but as long as there's no ignition source, you're not going to get this reaction. All right, so we got to modify that as well. So a successful collision will occur only if the colliding molecules have sufficient kinetic energy and the correct geometry. All right, what do we mean by that? Well, essentially, what are the factors that affect whether a successful collision occurs or not? The first thing is the amount of kinetic energy. Right? So the higher the kinetic energy, the more probable the collision will be effective. Because what has to happen is that, again, bonds have to break and bonds have to reform. And it's that initial breaking of the original bonds that requires this kinetic energy. So the more of it we have, the better we are. The second thing is that those collisions sometimes have to occur in such a way that the geometry is correct. Because if the geometry isn't correct, then we get some, basically the molecules just bounce off of each other. So if we have good geometry, then we end up needing the least amount of kinetic energy possible, and we get a successful collision. So if we have good geometry where the things can line up, and so when these collide, the circle and the triangle here, circle and the triangle here, and then they can break these bonds and move off, forming the two new compounds. However, if we have the collision happening in this form, this bond will break, but this one won't, and we don't have a successful collision. All right, so another example, collision 1. In this particular case, if we have this sort of geometry here, this fits in between here. It can break the bonds, and one of these can go to the one, and one can go to the other, and we've created the new bonds. This one here, if it's in this orientation, this isn't going to work. This doesn't fit in here. It can't collide with such a force that it'll break the bonds. Similarly here, similarly here. All right, so the geometry, the orientation of the molecules when they collide has a bearing on whether or not the reaction is going to be successful. So the reaction can only happen if, in the case of the acetylene in the previous molecule example, if the hydrogen end of the HCl bond meets the carbon-carbon double bond, any other collision doesn't work. The two simply bounce off of each other. All right, so let's stop there because that's a fair bit of stuff. Your textbook actually goes through this stuff in great detail. So have a read through that and then try some of these review questions in each of the sections. And that'll be the work for this week. Next week, we'll move on to some a little bit more complicated stuff. All right.